So the canonical, they call time computation relations between the field and the momentum are equivalent to the computation relations between the A's. So this for phi and 0, and for phi and 0, and for the diagrams, sorry, for the A's and the A's it's 0, and for the diagrams it's 0. And then of course you build your vacuum state as the state which is annihilated by all these A's. So a choice of a complete set UI gives you corresponds to the choice of a vacuum state. You can choose different UIs. That will mean that the AIs are going to be different, and that will mean that your vacuum state is different. Any questions about this? Okay, so I wanted to do two-point functions and calculate them in flat space-time. People are interested in going to curve space-time and black holes, so I'm not going to do the calculation of the two-point function in flat space-time explicitly. I'm just going to make a couple of comments about two-point functions. So without doing a calculation of this, these functions are important for particle detectors, which I'm not sure we're going to be doing. We will have time and people, with enough time and interest, we'll do it. Otherwise, we won't do particle detectors. And then you get the R set, the quantized expectation value of the central tensor, as a differential operator acting on a two-point function. Okay, so the expectation value, if you just take the expectation value of the field in a sort of quantum state that has a physical, has an observable meaning. If phi is a physical field. Now, if you evaluate the field, the expectation value of the field in a sort of excited state, so I'll call it nk1, it contains this number of particles with momentum k1, nk2, it also contains this number of particles with momentum k2, and so on. You evaluate the expectation value in this state, what is this equal to? So you replace the value of phi by this. And now you act on the state with these operators. So take this guy. This guy is just going to remove one particle of momentum I from this state. Okay? So let's suppose that you act that I is equal to K. So I here is just an index going through the whole labeling the modes of the field. Okay? So it can be K, all the different values of K. So in that case, it's a continuous index, it would be an integral over K. For a given value of I which corresponds to the value of K, you're going to have, suppose that it's K2, that I is equal to K2, you will remove one particle, you will have nk1 minus 1. Okay? And what's the product of this state with this state? It's 0. They're orthogonal. And so this will give you, this guy has, sorry, this would be the case, nk2. This has nk2 particles, this one has nk2 minus 1 particles, they're orthogonal, and so that will be 0. Similarly, this one will add a particle, let's suppose that I is equal to k2, that will give you, this is due to I, with I equal to k2, but if you act upon it with the adjoint, that will give you an extra particle. Okay. But again, this number of particles is different from this one, and so that's going to be 0. And you can do this for any different value of I. Okay, so the expectation value of the field phi in this state is 0. And this is for any number, state with any number of quanta for each one of the momentum. So the expectation value of the field is 0, but the expectation value of the field squared is not 0. If you just take the expectation value of the field squared in any state, is generally, that's not the same as squaring the expectation value of the field. Is generally different from taking the expectation value of the field and squaring it. It is a deviation from the mean. So in generally it's different from this, and it's also different from 0. So this is a manifestation of quantum fluctuations. There is a fluctuation about the mean value of the field. Okay? So this is observable, but it will be 0. Is this well defined?
Well, if phi is a distribution, so should not, because we have some kind of delta square.
That's right. It's an operator value distribution, and you can't just arbitrarily multiply distributions. The product of distributions in general it's not well defined. There are certain circumstances in which it is, but in general it's not. So you're right, that object is not well defined. We have to renormalize it in order to get something which is well defined. So it needs to be renormalized. So we know how to do this in flat spacetime. We do normal ordering. Okay, we put the creation operators to the left of the annihilation operators. Now, generally, that's not sufficient. What we need to do is first regularize and then renormalize by subtracting away some quantity. So what do we mean by regularizing? It's like giving a representation for this object. So if instead of evaluating phi at the same point x and multiplying by phi evaluate the same point x, we evaluate the two products, the two factors in that product, the two phi's, at different space-time points. That is going to be well defined. If we temporarily evaluated phi x and phi x prime, and then take the limit x prime goes to x, before we take the limit, these two distributions are not, they're not at the same time, at the same space-time point. So that's well defined. The divergences are only ultraviolet divergences. Remember, we saw that there was a quadratic divergence in momentum space for the Hamiltonian. There are ultraviolet divergences when you go to the frequency domain, when you go to the space-time points. It's divergence due to coincidence in the coincidence limit as x prime goes to x. So that's what we mean by regularize. We temporarily put the 2 points away. There's different ways of regularization. This is the so-called point splitting regularization, and there's other ways of doing it. There's that dimensional regularization, there's other ways of doing it. This is a standard way of doing it. We put the two space-time points away, then renormalize, so we subtract away something which diverges, but in a meaningful way. And after that, after we've renormalized, then we can take the limit x prime goes to x. I'm going to talk more about this, more probably about this when we do curved spacetime. So this is valid in curved spacetime as well. So a renormalization is not always sufficient. Often, one must previously regularize the ultraviolet divergent quantity. So phi squared is not well defined as an operator, or even as an operator by the distribution. And by phi x prime is so the point splitting regularization procedure consists of doing the following. You define the expectation value of the normal ordered phi squared. You you achieve this, you obtain this, now it's a regular object, by, as I say, taking the evaluation of phi squared at two different spacetime points. So first of all, you regularize it, and now we do the normal ordering. Okay, there's two columns here. That means normal ordering. That means renormalization. The way you carry out renormalization in flat spacetime. As I said before, that means placing the creation operators to the left of the annihilation operators, and that is equivalent, I showed the other lecture, that is equivalent to subtracting the expectation value of the Minkowski vacuum state. So that's the way I'm going to write it here. You subtract from it the value in the Minkowski vacuum state. So this renormalizes it. We're subtracting away a divergence in a meaningful way. And now the result of this subtraction now is regular, and now we can take the limit expanded first. Okay, so this guy here is called the Whiteman function. The g plus x expanded. It's called the Whiteman two-point function. Okay, so what equation does this satisfy? Does this object satisfy? It's a two-way function because it depends on two different spacetime points. What equation does it satisfy? Okay, homogeneous, inhomogeneous, delta.
Homogeneous with delta function.
Why is that?
It's like a function.
Why is that?
Why is
If you apply the Klein-Gordon operator here, and you apply it as at the point x, then this guy does not depend on x, it only depends on x prime. And so it only acts upon this, and this satisfies the homogeneous equation. So we have this, rather this, and so you have this as well. It's a homogeneous solution. And if you want to put in a mass, you include mass, and this is also true if you apply the operator on the point experiment. So the Whiteman function is physically relevant for particle detectors, and although it's not necessary to calculate the R set, it can be used to calculate the R set. So for calculation of the R set in the semi-classical equations. Because that's obtained as some, I write here, this symbol, this is just a second order, this is just a differential operator. I'm not going to give explicit value for this, but it's a differential operator acting on G plus sign. Okay, so another notation that you can see is that, so the plus here indicates what type of object it is. And you can put a psi as a superscript to denote this expectation value in this object is equal with the psi in the quantum state psi. So I'll put a psi here is an arbitrary quantum state. And then here you take the limit as expanded steps. In here, one would have to do renormalization just before renormalizing. Okay, but after renormalizing. Any questions about this? So I just wanted to give you a taste for the two-point functions. I was going to calculate in flat space-time explicitly, look at particle detectors, but I've been asked to go on to curve space-time as soon as possible, so I'm going to avoid that for now. If I have time at the end, we can go back, calculate in flat space-time, and see what happens to different particle detectors in flat space-time, maybe even in Schwarzschild space-time, and so on. But for now, I'm just going to leave it here, and I'm going to move on. So the next section is really, really important, and it's a consequence of things that I've been saying up until now. This at the start of the vacuum state, depending on the choice of constant frequency solutions, that has big consequences. Physical consequences. So the Aula effect is a consequence of that, and that's what we're going to go on to look at. And before we look at Bogoliubov transformations, which is going to manifest how the two vacuums that we've defined, or two different vacuum, are actually not the same. So like we said, the definition of a vacuum state is not unique. So in this sense, you can put vacuum in quotes if you wish, because it's relative to an arbitrary choice, arbitrary to some extent. So consider to complete an orthonormal sets of solutions of the field equations, of the homogeneous field equations. So U and V. So then you can write your field as a linear combination of the first set, HC for Hermitian conjugate, and then we have the inner product properties that I gave earlier on. You can do exactly the same thing with the second set. Okay, now the second set is V. So the coefficients don't have to be the same. Instead of AI, let's call them B, Bj. And the same thing V, V, G, V star, V star, V star. Okay, the same corresponding inner product properties. Now, both the U's and the V's are complete sets, so you can take any element of the V set and express it as a linear combination of the U set, because it's a complete set. So in particular, since UI forms a complete set, you can write one of the elements of the V set as a linear combination of the U set. And this is for some coefficients alpha and beta. This is called a Bogoliubov transformation, and these are called the Bogoliubov coefficients. Now, you can choose them arbitrarily. There's some constraints that this coefficient satisfy. So the Bogoliubov coefficients must satisfy some consistency conditions. We need to impose these properties for the inner product. So in particular, we impose this inner product, and all we do is express V, each one of the V's here, in this way. First one. Okay, and now we use the properties of inner product, which is that it's conjugate linear with respect to the first argument, and it's just linear with respect to the second argument. So these are just linear operations. We have sums, multiplications by a scalar, and so complex conjugate with respect to the first argument, it means we can take out the sums outside. So that's going to be a sum over I and a sum over M. Conjugate linear with respect to the first argument, that means we have to complex conjugate the alphas. We now apply, we know that this is just delta IM, and we know that this is just minus delta IM, and this allows us to go through one of the sums, and that gives this consistent solution. So that's applying this one. And now you can apply this one. I'm not going to do it in detail. It follows through in a very similar manner. So that's the other consistent solution. Okay, so now this relates the solutions. We've got consistency conditions for the Bogoliubov coefficients, but also we want to relate the operators, annihilation and creation operators, A's and B's, for the two that correspond to the two different complete sets. So what about the operators? So we saw I gave the expression for this. This is just a field. In the last lecture, I gave the expression for the coefficients. Okay, this just comes from the fact that the Vj Vm gives you delta Jm, Vj Vm star just gives you 0. So you just recover, you just pick this particular coefficient. And now you can do the same. Instead of evaluating phi in terms of the V set, you evaluate in terms of the U set. Now I can do the same thing again. The inner product is linear with respect to the second argument. So this guy is just delta, guy is the, you just go back here now, and this just gives you the, so you put the V, this expression for V in here, and you just recover the alpha. So this is alpha. I'm writing Vj now in that way, sum over I. The um and the u star does not survive, that gives you 0. The um and the ui gives you delta. It's conjugate linear respect to the first argument, so the alpha becomes convex conjugate. And similarly, this gives you minus beta j. And so the bj. So mixing operator, I'm here mixing operators and non-operators. They should remove, strictly speaking, you should remove this. And now I've got, bj is equal to this. This, and now we can promote this to operators. So this relates, in particular, the annihilation operator defined with respect to the V complete set in terms of annihilation and creation operators defined with respect to the U set. So you can already see that something, a little bit of magic has happened here. If the Bj annihilates a certain quantum state, doesn't mean that that state is annihilated also. Or let me rephrase it. If a certain state is annihilated by the A's, is it also annihilated by the B's? Everyone's saying no, why not?
Oh, there's a guy.
Right. But it could be that the betas are 0. So if the betas, so it's true that it's not true, that my statement is not true, if any of the betas is non-zero. Okay? If a state is annihilated by the A's, whenever you apply act upon it with a P, it's going to be annihilated by this bit, and it's only going to be annihilated by this bit if the beta is also 0. As long as one of the betas is non-zero, a state which is annihilated by the A's is not going to be annihilated by the B's. So the beta is really, these Bogoliubov coefficients really are bringing you extra particles. Okay, let me write this. So let's, like this guy, this quantum state denotes the U vacuum. And U vacuum state. So, by which I mean that is annihilated by the A's, which are the coefficients, the Fourier coefficients when expressed in the field in terms of the U solutions. And obviously, we speak of, so A diagram, I, we create a particle, a one particle momentum I with respect to this U vacuum state. These are as, we call this particle, U particle states. Of mode type I. And the same thing, similarly, we call this the V vacuum state. The state which is annihilated by the Fourier coefficients, B's, which are the Fourier coefficients, when expressed in the field in terms of the V complete set. Okay? And similarly you can create V particles by acting upon this vacuum state, this V vacuum state with B diagrams. So the big question is, what's the number of quantum particles? Now we need to distinguish between U particles and V particles. So of quantum V particles of mode type J in the U vacuum. So all you do is you take the expectation value in the U vacuum. I'm asking what's the content in the U vacuum. So I'm taking the expectation value of the number operator in the U vacuum. But one number operator, I'm asking about V particles. So I want the number operator in relation to the V vacuum state. Calculate that expectation value when the field is in the U vacuum state. So this is the number of particles, of V particles of mode type J. So I want to know the expectation value of this number operator when the field is in the U vacuum state. So now the Bogoliubov transformations allow us to get this. Okay, so let's operate here. Now, in principle, we don't know how the B's act. The B's act on the U vacuum state. In order to know how that happens, we re-express the B's in terms of the A's, because we do know how the A's act on the U vacuum state. The U vacuum state is defined as the state which is annihilated by the A's. So the A acting on the U, that's going to be zero. By definition of the U vacuum state. Obviously, if you take the adjoint of this, that also means that that this is zero. That's just taking the adjoint. So that means that the A dagger acting on the bra for the U vacuum state, that's going to be 0 as well. This by acting here, and this guy is by acting on this one here. Okay, so now we have some of our I and K of the minus and the minus cancel out. J, I, the star, J, K, and now the A, I, so we apply this. A dagger on 0U gives you the U1 quantum state with mode type K. And similarly, the A dagger I on this gives you U1I. And this is 0 if I and K are different from 0, and it's a delta term. And it's not 0, it's 1 if I and K are the same. So this just gives you delta I and K. It allows us to go through one of the sums. And so we have this. Okay. So the U vacuum state in general contains V particles. This number of V particles. If it happens to be so that the betas are 0, then it does not contain any V particles. But if any of the betas is not 0, then it does contain some V particles. So that's for specific mode of type I. You can then sum over all the different mode types. Total number of V particles in the U vacuum is sum over I and J, beta and J. So the U vacuum and the V vacuum are equivalent states, even only if, and I get 2 F's means even only if it's a condition going in both directions, beta ij is equal to 0 for all i's and j's. So this is everything. This is Hawking radiation. This is the Ongo effect. Everything is based on this. Question. I don't want to get into this, but just that I want to comment on it. Is this finite, or is it, or can it be infinite, or?
Looks like
in principle, it can be. It will depend on the betas, if the betas are 0 or not. But in general, there's potential for it to be infinite. And in fact, we've got 2 sums there, which in principle are infinite sums. And in fact, typically they're going to be integrals. These indices again can relate to continuous indices or discrete indices. Now, I don't really want to get into this, but you've got, what we want is, a unique, what we don't want is unitary equivalence. If there is unitary equivalence between the choice of the U complete set and the choice of the V complete set, that means you can describe your physical system using whichever set you want. If that's not the case, you're in trouble. Okay? And one can prove that unitary equivalence happens even only if this sum is finite. Now, in general, it's not going to be finite, and so there's issues with this. And the way to make this rigorous is by going to algebraic QFT, which I'm not going to do. You can look at the book by Wald, the little red book by Wald, does this. So if you want to do things rigorously, you go into that, and things are mathematically well posed. As we're doing it, it's not quite the case, but it's not going to affect. We're not going to let it affect us anyways. So, in the case, this double sum, being equal to infinite, that means that the two different vacuum, and when I say two different vacuum, I mean everything involved with this. The choice of positive frequency modes and the choice of Hilbert space. We've got a construction of a Fock space different for the two different choices of vacuum space. So those two Hilbert spaces will be unitarily equivalent if this is finite. So there are two different vacuum lead to unitarily equivalent, inequivalent. If that double sum is infinite, there are inequivalent representations of the canonical combination relations. And leads to unitarily inequivalent Fock spaces. So unitary equivalent just means that you've got a unitary operator that maps the operators of one Hilbert space to the operators of the other Hilbert space. And if that's the case, then you can use the two different Fock spaces to describe your physical system. If they're not unitarily equivalent, you don't have that property, and so you're in a bit of a pickle, as it's said in English. So there's two issues with what's happening here. One is of a more physical type, the other one is of a more mathematical type. The one physical type is the one that interests us. It's the fact that two different complete bases will lead on to different vacuum states, and so different observers will see different vacuum states, essentially. That's what physically, the physical consequence of this. Another one is of more mathematical type. In order to cure this, so this is, in order to cure this, you can go to algebraic QFT that can deal with this. Where really the fundamental things are the algebraic relations that the operators satisfy. Any questions? Okay, so the next step is to apply this to flat space-time and see the unglued effect. Before we do this, we're going to have an orgy of Penrose diagrams in this course. So we might as well be acquainted with them. Okay, you have to be acquainted with Penrose diagrams. So I'm going to do it in detail in the case of 2D space-time. So this is Penrose diagram and Cauchy evolution. I'll see if I do this explicitly or not for in Schwarzschild space-time. Okay, so I'm going to do it for 2D flat space-time. Consider two-dimensional flat space-time. Okay, so t and y are just Cartesian coordinates. So the metric is just -1 plus 1, diagonal. And Penrose diagrams, the crucial thing about Penrose diagrams is that it captures the causal structure of your space-time. So you really wouldn't, the basis of this are the null geodesics. So you want to go to null coordinates. Okay, so what are the null coordinates? In flat space-time, the geodesics are just straight lines in the on the Cartesian plane. So the null coordinates are t minus y and t plus y. Okay, so you've got y and t. This is your line column. Going through this point x of the space-time. Okay, at 45 degrees. V and U are both ranging over the reals. Okay, so that's also T is U plus V over 2, and Y is V minus U over 2. So in here, you've got du squared plus dv squared minus du squared. Sorry, du minus du. That's just dv squared minus du squared. Sorry, multiplying it, not the division. So it's minus dt du, so that's du plus dv. Jesus. Okay. So the du squared cancels out with this one, the dv squared cancels out with this one. You've got minus, that's going to be plus 4, so that's du dv. sorry, it's going to be minus du. Okay? So that's a different way of understanding line codes. Whenever you've got u equals constant or v equals constant, that gives you the line element is equal to 0, and so that corresponds to null geodesics. Okay? So null geodesics correspond to u equals constant or v equals constant. Okay, now all these guys range over the reals. What we want to do is compactify this. We want to put the whole of the space-time on the blackboard. So the range of u and v going from minus infinity to infinity, we want another quantity, another coordinate that ranges over a finite range in order to put the space-time on our blackboard. So you compactify by defining some capital U and capital V in this way, and then capital U and capital V range over this finite range. Minus pi over 2 and pi over 2 are not included because that will be u and v equals infinity, which is not a real number, it's not a point in space-time. And so you take the derivatives that's what you get. These are still in null coordinates. We want to get the equivalent of this capital U and capital V in terms of Cartesian coordinates, compactified Cartesian coordinates, if you wish. These are compactified null coordinates because capital U equals constant still corresponds to little u equals constant null geodesic. These are still null coordinates. Compactified null coordinates, we want to get compactified Cartesian coordinates. So define capital T as capital U plus V and capital Y as V minus U, and that will range between minus pi and pi and minus pi and pi. Okay, and then we have the line element is written product of these two things, and you can rewrite it again in terms of these compactified Cartesian coordinates. In this way. So the Penrose diagram is a diagram where the axes are these compactified Cartesian coordinates, T and Y, capital T and capital Y. It's called Penrose-Carter diagram. So as I say, capital Y, capital T, null geodesics, well, if these are T and Y, then these are V and U. Just from this. Null geodesics correspond to little u or little v constant, which is the same as capital U or capital V constant. So null geodesics are still at 45 degrees in Now, capital Y goes between minus pi and pi. And so does T. I'm really bad at drawing things. So this diamond is the whole of your spacetime. Okay, this is capital U pi over 2, capital U minus pi over 2, capital V pi over 2, capital V minus pi over 2. If you are at a point here and you emit light, light will go in this direction. Always 45 degrees. Capital U constant or capital V constant, depending on which direction light is going. T equals constant is a curve of this type, and Y equals constant is one of this type. Okay, so as I say, no geodesics are going at 45 degrees. So this tells you there's a null geodesic. This tells you that all null geodesics end up either on this side of the diamond, or on this side. So this guy, this side is called scribe plus subscript capital R. This is T equals infinity, U equals infinity in Cartesian coordinates, V equals infinity in null coordinates, capital V equals pi over 2 in compactified null coordinates. And this one here is scribe plus L to the left, plus because it indicates the future. This is T equals infinity, Y equals minus infinity, U equals infinity, capital U equals capital U. Similarly, all null geodesics must originate. If you extend the geodesics to either this side of the diamond or this side. So this is called scribe minus right. And it's the same thing with T equals infinity, minus infinity instead of plus infinity. And the same thing here. This is scribe minus left. So T equals minus infinity, Y equals minus infinity, U equals minus infinity. Sorry, V equals minus infinity. And capital V equals minus pi. Okay, so where do time-like worm lines end up?
The other one.
At the upper point. So we call this I plus. Do all time-like worm lines end up light loss?
Oh, okay.
Well, they come from I minus do all time-like war lines come from I minus and n dot I plus? Sorry?
It looks like, I think so.
You think so? Any other opinions?
In principle, I would say that no. I would say that it could end up in I plus, but that is quite plus.
How could that
Because
happen?
it's inside of the level.
So good. A time-like war line could end up here?
Yes. In,
Why is that?
well, if they are inside of initial icon, so they can, whenever they want, they can here or here, they just not have to pass the icon.
Yeah. So note that they asked not time-like geodesics, but time-like war lines. All time-like geodesics will end up there. But an accelerated war line, and in fact a lunar observer, which is an important accelerated observer, does not end up here. Its velocity asymptotes to infinity, and so it asymptotes to Scribos. Okay? So we're talking about geodesics here. So future null infinities, past null infinities, all future directed null geodesics begin at begin at sky minus and end at sky plus. And as I say, I plus, I minus, they're called future time-like infinity and past time infinity, all future directed time-like geodesics begin at I minus and end at I plus. Time-like geodesics, not necessarily accelerated warlines. And finally, you've got the space-like infinities. So this guy here is I0 right, and this one here is I0 left. So I0 left and right are space-like infinities. All space-like geodesics begin and end at I0. Now the really crucial thing here is the causal structure of the space-time. If you're an observer, if you emit light here, or emit a signal here, and it propagates along null geodesics, it will reach out to these points, and you can say send signals that don't travel the speed of light, that travel slower than the speed of light. If you send them through a massive field, for example, they will travel slower than the speed of light, and so they can connect you can reach any point here, any point within the 45 degrees wedge. But you'll never be able to reach a point below the 45-degree wedge, because that will require the signal traveling faster than the speed of light at some stage. So that's really the crucial thing. It tells you the causal structure is. Because null geodesics are at 45 degrees. Any questions? Just a little, so I encourage you to play around with Penrose diagrams and look at them in other spacetimes. This 2D flat spacetime, there's this funny feature that there's a left and a right. But all the points are here. It's a two-dimensional diagram. It's two-dimensional spacetime. If you go to 4D, flat spacetime, the Penrose diagram will be this. This is chi plus, this is chi minus, this is I0, and this is I plus, and this is I minus. Now, in here, the spatial coordinate is no longer a Cartesian type of coordinate that goes from minus infinity to infinity. It's just the radius. Okay? That's why you've only got r equals 0 here, and then you've got r equals infinity here, t equals infinity, r equals infinity here, t equals minus infinity. Each point here, each point is a two-sphere. It has a topology of a two-sphere. Okay? So we're ignoring, this ignores theta and phi coordinates. So what does this mean? You've got a null ray coming in from radial infinity. It reaches r equals 0. This is flat space-time. R equals 0 is a totally arbitrary point. Flat space-time is just homogeneous and isotropic. You just choose your coordinates to be based, centered on a certain arbitrary point in your space-time. What happens here? Nothing happens here. The light ray just goes through r equals 0. What happens is that theta or phi, the angle changes. Okay? If, say, phi goes from 0 to phi equals 2 pi. In other words, it reaches r equals 0, and then it continues going this way. The radius now, as it reaches r equals 0, the radius, as it goes through it, the radius now starts increasing. If this duster is r equals 0, the center of the spatial coordinates, the null geodesic, the radius of the null geodesic decreases, it reaches r equals 0, and then the radius continues increasing. It's just that the angle just changed from phi equals 0, phi equals 2 pi. You can see the angles here. But we represent it by saying it's reflected through r equals 0. All it means is just it's going through r equals 0. Note that you could have a space like geodesic in flat space, 4D flat space time, that it's a straight line. It goes like this, it does not go through r equals 0. So in that case, it does this. But you have in the case of a null geodesic which does not go through r equals 0, you'll have a null geodesic doing this. Because the theta and the phi coordinates are changing. So whenever we say that the null geodesics are doing this, so this is true in null geodesic, essentially. Future there are null geodesics. This is from 2D. In a 4D space-time, it's only the radial null geodesics that are doing that. Okay, the non-radial ones, the ones that are not going through, they don't do that. But the radial ones are the important ones. They're really the ones that give you the causal structure. curve diagrams and Cauchy evolution. So just a couple of words on Cauchy evolution. Well, first of all, a causal curve is just a timeline or null curve. It's a curve whose tangent vector is everywhere. Time number null. You can change from time to null if you wish. You wouldn't be geodesic, and a Cauchy surface for a space-time n. So these are general definitions. Is a space-like hypersurface which is intersected exactly once by every inextendable causal curve in M. Inextendable just means that there's no future or past end point. Okay, and now a space-time is globally hyperbolic. Even only if it possesses a Cauchy surface. So, in flat space-time, t equals constant is a Cauchy hypersurface. Okay, is this a Cauchy hypersurface? Hands up for the people who think this is a Cauchy hypersurface. Wow, a shiny one.
I know it isn't, but I can just explain why. So